Our lecture on basic concept on polymers. Today we are going to start with polymer classification. You are acquainted with some names of polymers in different ways, sometimes plastics, sometimes fibers, sometimes rubbers, sometimes thermoplastic polymers, sometimes thermoset polymers, sometimes natural polymers, sometimes synthetic polymers, like that. So, let us see the classification scheme of polymers, how the polymers are classified from various angles. So, there are bases of classification accordingly, and we find different polymers, polymer types are known to us. Say, if we classify the polymers on the basis of origin, that means the source, genesis of the polymer, we will find there are three categories of polymers: natural polymers, semi-synthetic polymers and synthetic polymers. What are natural polymers? We will see later. Let us see what are the different classes of polymers here. On the basis of origin, it is natural, semi-synthetic and synthetic polymers. From thermal behavior of polymers, we find there are two categories: thermoplastic polymers and thermoset polymers. On the basis of mode of formation, means how these polymers are synthesized, the basis of principles of polymer synthesis, we find there are two categories of polymers: addition chain polymers and condensation chain polymers or condensation polymers. On the basis of line structure, we find there are linear polymers, there are branched polymers, there are cross-linked polymers. And on the basis of application and physical properties, we find rubbers, plastics and fibers. Of course, there are differences in these different names in each category, we will explain later. Then on the basis of tacticity, tacticity means if you think of a polymer molecule, there may be side groups, that means the disposition of side groups that gives a geometric shape to the molecule, geometric configuration to the molecule, and we get three different types of polymers: isotactic polymers, syndotactic polymers and atactic polymers. Then crystallinity, on the basis of crystalline structure, on the basis of morphology, we can say we can have amorphous polymers, semi-crystalline polymers and crystalline polymers. Polymers can also be classified in other ways too. I have not shown here, but you can note down. Say polymers can be homopolymers and copolymers, and copolymers can be again alternating copolymers, random copolymers, block copolymers, graft copolymers. So, various homopolymers and copolymers are existing. Now, let us come to little of these classifications. On the basis of origin, I told you there are natural polymers, semi-synthetic polymers and synthetic polymers. In the natural category, there are many polymers naturally occurring, that means synthesized or prepared by various agencies of nature. What are the agencies? Plants and animals. Plants synthesize some polymers. So, like say natural gum is a polymer. You see there are various plants available. If you make an incision on the bark, you will find some exudation is there, some fluid is coming out. Now, that fluid contains certain polymers. You are acquainted with a fluid coming out from say jackfruit tree. If you make an incision on the bark of the jackfruit tree, you find a milky fluid is coming out, and that also contains a polymer. And there is another plant known as Moringa oleifera. Say we get a vegetable from that drumstick vegetable. If you again there make an incision on the bark, you will find that some gum is coming out, that is also contains some polymers. Apart from all those things, if we look into the plant kingdom other way, say wood contains a polymer, cellulose. Wood is a composite of cellulose and lignin, where cellulose is the fiber dispersed in a continuous matrix of lignin. Lignin is the binder and cellulose fiber is the reinforcing member over there. So, we will find there are cellulose, starch also is a polymer, and in animal origin we find proteins, different types of proteins, they are also polymer. That day somebody was asking me, sir, how can we define this as a polymer? That can be a random copolymer type, because different amino acids are linked in one molecule in different sequences. So, that is also a polymer. We can consider that as a copolymer, but that is a polymer having peptide linkages. So, we call that a polypeptide. Silk, wool, these are from animal origin, silk, wool, and natural rubber. Natural rubber is obtained from a tree known as hevea tree. Hevea brasiliensis. This is a tree, big tree. If you make an incision on the bark, it oozes out, exuded out a liquid known as a latex, where the polymer constituent of this latex is cis-1,4 polyisoprene. This is excellent polymer. It is a unique gift of nature. The molecular weight of this polymer present in this natural rubber latex is very high, maybe 10 lakhs, 15 lakhs, like that. And its chemical formula is this is the 1 unit of cis 1,4 isoprene unit repeated in sequences. That is why it is called cis-1,4 polyisoprene. Sorry, this is trans. I am sorry, this is trans. This is trans. Trans 1,4 polyisoprene, and cis form is this trans form is known as gata parcha. It is plastic in nature. And this cis form is elastomeric. That is because of this cis trans configuration. How? You see, this is cis configuration. So, if you look into this molecule, you will find it looks like this. That means, this segment or this unit gives a bent configuration, whereas in case of this trans one you see there is a linear configuration. So, it leads to higher molecular packing. So, it gives a plastic type of molecules material, whereas this is elastomeric. Now, you will understand the details of this thing later. It is little difficult to understand this from the molecular configuration, why we are calling this as elastomeric, this is a plastic, but just I have mentioned this thing. And polyhydroxyalkanoates, what are polyhydroxyalkanoates? These are bacterial polysaccharides. Known as bacterial polysaccharide. This is a naturally occurring polymer. This polymer finds extensive use today in biomedical engineering field. This is biodegradable bacterial polysaccharide, so and so forth. So, you will find plenty of examples of naturally occurring polymers which are friendly to nature, degradable by natural organisms, bioorganisms, bacteria, fungi, insects. That means these can behave as a food for those microorganisms. So, they are degradable. Next category is synthetic polymers. When the demand for polymers could not be supported by the naturally occurring polymers or natural polymers, say natural rubber and other gums etc., was not sufficient enough, then people thought of preparing by an artificial route different types of polymers, and for which they found some petroleum products, petroleum base. If time is permitted, then I shall discuss something about petrochemicals. What are petrochemicals? How these polymeric raw materials or monomers are obtained from petrochemicals, I will discuss. Some of you might have read in your previous course. So, synthetic polymers, since these are prepared by synthetic route, artificial means in the laboratory, in the industry, in chemical reactors, in polymerization reactors, we call them synthetic polymers. Plenty of examples can be cited. Say polyethylene, this is the first example, polyethylene, PE. There are various grades of polyethylene, low density polyethylene, high density polyethylene, linear low density polyethylene, very low density polyethylene, and ultra high molecular weight polyethylene. You see, large number of grades are possible from polyethylene. Next comes polypropylene. You know the formula of polyethylene, you know the formula of polypropylene. How they are synthesized? They are synthesized from ethylene for polyethylene and propylene for polypropylene by applying sufficient polymerization conditions in presence of catalyst and temperature. There are various grades of polypropylene again. You will see in next classification, atactic polypropylene, isotactic polypropylene and syndiotactic polypropylene. So, this way you can get various grades of polypropylene. PVC, polyvinyl chloride, synthetic polymer made from vinyl chloride monomer. PAN, polyacrylonitrile, PAN. You have to be acquainted with these abbreviations of these polymers. PAN, polyacrylonitrile. PMMA, polymethyl methacrylate. How to write the structure of PMMA? Formula of PMMA Repeat unit formula of PMMA, CH2, C, substitute one hydrogen of this carbon by methyl group, substitute another carbon, another hydrogen of this carbon by an ester. N number of times, where this N is the degree of polymerization. N is the degree of polymerization. Depending on the value of N, we can have an idea of the molecular size, how big it is. Very big, high value, high molecular weight, low value, low molecular weight. Low molecular weight polymers we call oligomers. Oligo means lower, oligo means lower number, smaller number, oligomers. Say SBr, what is SBr? It is a Buna rubber. It is a copolymer of styrene and butadiene. What is polystyrene? Again, to write the formula of styrene, polystyrene, it is very easy. You write this CH2, CH, a phenyl ring, this is polystyrene. What is polybutadiene? You know what is butadiene? Butadiene, you polymerize, sorry, again it can undergo cis trans configuration. So, there can be linkage is a 1, 2, 3, 4, 1,4 linkage, this is 1,4 cis polybutadiene, 1,4 trans polybutadiene. You can have either 1,2 linkage or 3,4 linkage, there you will have 1,2 polybutadiene or 3,4 polymer butadiene, that is called vinyl unit, like this. This is also polybutadiene, 1, 2 or 3, 4. This is 1, 4. This is 1, 4. This is 1, 2 or 3, 4. Any of same thing, same, it is symmetric. 1, 2 or 3, 4. Both can say polybutadiene. So, and Cr is chloropene rubber. Polychloropene rubber. Polychloropene rubber. You know what is the chloropene? If you can remember formula of isoprene, you can remember the formula of chloropene. CH2 this is polychloropene, PCP or Cr or neoprene, trade name is neoprene, neoprene rubber. NBr, it is a copolymer of acrylonitrile this is acrylonitrile and copolymer of acrylonitrile and butadiene nitrile rubber. nitrile or NBR rubber, NBR, PBR, polybutadiene, you have seen earlier polybutadiene, PBR or BR, polybutadiene rubber. Butyl rubber, it is again a copolymer, where the co-monomer percentage is very small. Butyl rubber, it is a polymer of polyisobutylene. Where N is only 1 to 3% co-monomer percent. This is actually butyl rubber. Okay. Silicone rubber, silicone rubber, polydimethyl siloxane, polydimethyl siloxane. It is a heat resistant polymer, heat resistant rubber. Polytetrafluoroethylene, you know what is polytetrafluoroethylene? Fluororubber, say fluororubber is a copolymer of say maybe say tetrafluoro ethylene and hexafluoropropylene. There may be other types of fluororubber possible. Again we can have fluorosilicon rubber. Just replace these hydrogen atoms by fluorine, you will have fluorosilicon rubber. EPDM, ethylene propylene rubber. EPDM is a copolymer of ethylene and propylene. Ethylene leads to polyethylene, propylene leads to polypropylene, both are plastic, but when these two monomers are polymerized together, they form a copolymer known as ethylene propylene copolymer, and that is elastomeric in nature. It develops rubbery properties. The reason I will explain later. And there is another monomer present, that is actually a diene monomer. For the purpose of introducing some cross linking site, a diene monomer is introduced along with ethylene and propylene. So, that is known as EPDM rubber, and EPR, polyvinyl alcohol. Polyvinyl alcohol, it is obtained from say 90% hydrolysis, 8 to 10% acetate group remains in polyvinyl alcohol. Polyhema, if you can remember the formula of polymethyl methacrylate, there methyl acrylate, in place of methyl acrylate, if you take hydroxymethyl acrylate, you will get polyhema. You can write down the structure. In place of methyl acrylate, you have to write hydroxymethyl acrylate. Poly N isopropyl acrylamide, it is a modern polymer known as Mod polymers, known as stimuli responsive polymer, known as thermoresponsive polymer, poly N isopropyl acrylamide. Before that, you see what is acrylamide? Polyacrylamide, PM, acrylic acid, CO, N, H2, polyacrylamide. So, here also you write down this formula, N isopropyl means to this give one isopropyl group, one H remains. So, this is actually poly N isopropyl acrylamide. It is a thermoresponsive polymer. It undergo phase transformation from, it can shrink or swell by change of 1 degree temperature. It is so thermoresponsive, and this polymer finds extensive use in biomedical engineering field, drug delivery, pulsatile drug delivery, targeted drug delivery with the change in temperature. People are making artificial pancreas out of this polymer, artificial pancreas or controlled drug delivery devices using this poly N isopropyl acrylamide. Okay. Then these are one category of polymers. In this synthetic class, there are other polymers too available, possible to synthesize. Say polyester, you are acquainted with polyester because the garments you are wearing, that is made of polyester fiber. Mineral water bottle, beverage bottles made of polyester, films made of polyester. You are acquainted with a polymer PET. PET is a polymer used for making bottles, films, say overhead transparency films, they are known as mylar film, that is made of polyethylene terephthalate. PET. What is polyethylene terephthalate? It is a reaction product of ethylene glycol and terephthalic acid. What is ethylene glycol? This is ethylene glycol. What is terephthalic acid? Terephthalic acid. So, these two, this is an alcohol and acid. You know, when an alcohol reacts with an acid, the product is an ester with the elimination of a small molecule as byproduct. Here also, if you take a catalyst and apply heat, you will get this unit is repeated along the backbone chain. Thank you. One more CS would be there. This polymer can also be made from by the reaction of ethylene glycol and dimethyl terephthalate by ester interchange reaction. You can take ethylene glycol EG and DMT, dimethyl terephthalate, will get same PET polymer. This is a polyester. You can have, this is a saturated polyester, you can have unsaturated polyester too. If you react malic anhydride with ethylene glycol or other alcohol, you will find unsaturated polyester. Today unsaturated polyester finds a large consumption in laminating industries, in composite industries, and then polylactic acid, polylactate, polylactides, polyglycolic acids, copolymers of polylactic acid, polyglycolic acid, polylactide co-glycolide, polycarbonates, polyamides, polycarbonates, this polycarbonate is a polymer, it is a transparent polymer, colorless transparent polymer, or you can make it colored also. It is strong, it is resistant to degradation at elevated temperature. So, these are used for making baby feeding bottles which can be sterilized. Polyamides, different types of nylons are possible. As you have seen here, polyamides, nylons can be both aliphatic and aromatic, depending on what reactants you have selected. You can have aliphatic nylons like nylon 6, nylon 66, nylon 610, nylon 11, nylon 12. Say nylon 66 is made from hexamethylene diamine and adipic acid. So, that this is adipic acid and hexamethylene diamine reacts This is nylon 6,6. Why nylon 6,6? From the acid side there are 6 carbon, 4, 5, 6. From the diamine side there are 6 methylene groups. So, that is why it is called nylon 6,6. You can get nylon 6 from caprolactam, epsilon, sorry, ring compound. Oh, there will be one more C. I am sorry, one more C. Nylon 6, caprolactam ring compound, caprolactam, nylon 6, or you can have the same nylon 6 from omega amino caproic acid, is open chain compound, both lead to nylon 6. Formula is nylon 6. Yes, yes, it is nomenclature epsilon caprolactam. This compound is known as, this ring compound is known as epsilon caprolactam. Okay. Look at the IUPAC nomenclature. Okay. Aromatic polyamides say aramid polymer, aramid fiber is aromatic polyamide. What is that? That is made from terephthalic acid and paraphenylene diamine. What is terephthalic acid? You have seen earlier. I am writing this way. Paraphenylene moiety, terephthalic acid moiety, one CONH group has come. So, this has the functional group of amide functional group CONH is aromatic polyamide. You can have, you can take meta substitution as your meta isomer also, then it cannot lead to a fiber, but that is you can get film or other plastic, but these are high temperature polyamides, aromatic polyamides. Okay. And polyimides, these are polyamides. Polyimides are further stronger polymers, heat resistant polymers, thermostable polymers, polyimides. Say actually this is pyromellitic dianhydride, PMDA, pyromellitic dianhydride. When reacted with paraphenylene diamine, we get an aromatic polyimide. This is the imide functional group.
Oxygen have triple 3 sigma 1.
Here no, actually sorry, here nitrogen will come. I am sorry, I should not show any bond here. So, keep like this anhydride oxygen, keep here oxygen, then of course you have to write one more unit in order to show this thing, one more unit this side. So, this is the amide linkage, all the 3 valencies of nitrogen are satisfied. That way we can get different types of polyimides, aromatic polyimide polymers. They are further thermally stable polymer, and it leads to a double strand polymer like this. If you imagine this way, it is called a multi-strand polymer or double strand polymer. So, if you find, we consider this as like this. So, this is a chain, carbon chain, this is another carbon chain where these 2 chains are linked, interlinked like this. No, linker molecule means, you see, this is a phenyl ring, this is an imide ring, phenyl ring followed by imide ring, followed by phenyl ring, followed by imide ring, followed by phenyl ring. So, it is looking like this ring. Okay. Multi-strand polymer or double strand polymer. In case of polyethylene, what you have seen? A single strand. That is why that is flexible, but these polymers are very rigid, stable to very high temperature because of this thing. Because in case of this polymer, if thermal energy is applied to this polymer, it can break anywhere the carbon backbone chain. But here, if it causes breaking at any point here, probability is like this. So, still then the structure will be maintained, because these are interlinked with, this chain is linked with to this chain by these interlinking bonds, ring structure. The probability is very less that this will break and all these interlinks will also be broken, rings will also be paralyzed. That possibility is remote. That is why this is considered as a, or in fact they have shown very high thermal stability. In fact, they are known as high performance polymers in spacecraft applications. Say this polymer is used for making composite with carbon fiber polyimide composite. It is mechanically strong as well as thermally durable, thermally stable. Do you understand? Similarly, polysulfones, polyether ketones, you will come across the structures of those polymers. Then epoxy polymers, epoxy polymers. You know araldite. What is araldite? It is a 2-pack polymer, 2-pack system. One pack is the resin polymer and the other pack is the hardener, cross linker, 2-pack system. When these two are mixed, it sets to a rigid structure, insoluble, infusible structure, insoluble and infusible form, that epoxide polymer. Epoxy polymer is used extensively in composite structures, where glass fiber is used as a glass fiber or some carbon fiber or any other fiber is used as reinforcement, which is dispersed in epoxy resin matrix. We get epoxy reinforced composites, epoxy fiber is reinforced composites. Next comes another important class. Examples of polymers are phenolic resins. Polymer of phenol and formaldehyde. I should write this way: phenol formaldehyde resin, PF resin. What is this? You know, this is phenol, this is phenol. Now, at this point I must mention one thing. For getting a polymer, for synthesizing a polymer, minimum requirement of functional groups are 2. So, if you want to make a polymer, you have to select a monomer which must have 2 functional groups. Say hydroxy acid, one hydroxy acid can lead to a polyester. Amino acid can lead to a polyamide, or diamine having 2 amine functional groups can react with a diol having 2 hydroxyl functional groups. So, bifunctionality is required. That means, the functional groups should be minimum number of functional groups should be 2, it can be more, 2 or more. If there are more than 2, then there are certain other cases we will find later. But I like to mention here this phenol. How many functional sites are there? 1. One of you are telling it is 1 and some other is telling as 6. It is trifunctional. Two ortho and 1 para position. These are reactive positions in this phenyl ring. So, trifunctional. So, this trifunctional phenol reacts with formaldehyde. Is it monofunctional? Formaldehyde? No, it is bifunctional when it is dissolved in water. So, formaldehyde formalin. In formalin, we find this kind of chemical unit. So, when this react with I am sorry. I should not use a bracket. Methylene glycol.
So phenol is trifunctional.
Okay. Now, when this reacts,
So white cannot bind with metabolism.
you have to go through that isomerization of this phenyl ring. Here is no scope to discuss all those things. I am going little in depth for your understanding, because this is such a course. I have to cover huge things, huge areas, and since in future I may not get access to describe all these things. So, I am telling, just referring these things. So, this is trimethylol phenol, this is trifunctional, this is highly reactive. Again, when it further condenses with formaldehyde, means the methylene glycol, it leads to a polymer having branches or cross-link structures, and ultimately we get 3 stages of this phenol formaldehyde products. In the stage A, in stage B, we will get linear PF resin with further formaldehyde, we will get branched PF resin, and in stage C, we will get branched PF resin, So, this is PF. Similarly, we can have amino resins, melamine formaldehyde, melamine reacts with formaldehyde, we get MF. It also passes through A to B to C. Similarly, urea formaldehyde, it also leads from A to B to C stage. So, all these are leads to a cross linked polymer structure at the end. Alkyd resin is a polymer, again is a polyester, it is again a polyester. Alkyd resin is a polyester made from phthalic anhydride and glycerol. Next comes semi-synthetic. Now, you have seen what are synthetic polymers, you have seen what are natural polymers. So, if we do certain kind of modification, carry out certain kind of chemical modification on natural polymer, we call it semi-synthetic polymer. Say cellulose is a natural polymer, we can make derivatives of cellulose, we can make nitro derivative of cellulose, say cellulose nitrate. Cellulose nitrate is an explosive material, you know, cellulose nitrate, explosive material, but when cellulose nitrate is plasticized with camphor or other plasticizer, it leads to a plastic. Spec frame, comb, Photographic films, those are made from cellulose nitrate plastic. So, there is a derivative. Similarly, viscose rayon, regenerated cotton is a viscose rayon, or cellophane film. You have seen cellophane, it is nothing but regenerated cotton. Cellophane film you have seen in the market, you have used also in various different colors. We get thin transparent films in different colors, red, blue, green, yellow, etc. That is nothing but cellulose, regenerated cellulose. What is regenerated cellulose? Say cellulose, if you consider this cellulose as ROH, having cellulose units contain hydroxyl groups, when that is reacted with carbon disulfide in presence of alkali, it actually forms a xanthate, sodium cellulose xanthate. When this sodium cellulose xanthate, it actually poured on an acid bath, the cellulose is regenerated. Okay. So, this is regenerated cellulose, cellophane, etc. So, up to this much. If you have any queries, you can ask me.